The third law of thermodynamics and absolute entropy. As we consider a second law analysis of chemical reactions, we face the same problem we had with the first law. What base should be used for the entropy of the various substance? What base should be used for the entropy of the various substance? This problem leads directly to a consideration of the third law of thermodynamics. The third law of thermodynamics was formulated during the early 20th century. The initial work was done by primarily W. H. Nernst. And Max Planck. '80, 58, 90, 47. The third law deals with the entropy of substances at absolute zero temperature, and in essence states that the entropy of a perfect crystal is zero at absolute zero. From a statistical point of view, this means that the crystal structure has the maximum degree of order. Furthermore, because the temperature is absolute zero, the thermal energy is minimum. It also follows that a substance that does not have a perfect crystalline structure at absolute zero, but instead has a degree of randomness, such as a solid solution or a glassy solid, has a finite value of entropy at absolute zero. The experimental evidence on which the third law rests is primarily data on chemical reaction at low temperature and measurement of heat capacity at temperature approaching absolute zero. In contrast to the first and second laws, which leads respectively to the properties of internal energy and entropy, the third law deals only with the question of entropy at absolute zero. However, the implications of the third law are quite profound, particularly in respect to the chemical equilibrium. The relevance of the third law is that it provides an absolute base from which to measure the entropy of each substance. The entropy relative to this base is termed the absolute entropy. To increase the entropy between absolute zero and any given state can be found either from the calorimetric data or by procedure based on statistical thermodynamics. The calorimetric method gives precise measurement of specific heat data over the temperature range. The increase in entropy between absolute zero and any given temperature can be found either from colorimetric data or by procedure based on statistical thermodynamics. The colorimetric method gives precise measurement of specific heat data over the temperature range as well as the energy associated with the phase transformation. These measurements are in agreement with the calculation based on statistical thermodynamic and observed molecular data. Table A10 gives the absolute entropy at 25 degrees centigrade, 1/10 megapascal. Pressure for a number of substances, table A9. Give the absolute entropy for a number of gases at for the substance and absolute entropy at 1/10 megapascal for various gases at different temperature. For gases, the number in all these tables are the hypothetical ideal gas values. The pressure P0 of 1/10 megapascal in terms the saturated state pressure, standard state pressure. And the absolute entropy as given in these tables is designated S bar star. The temperature is designated in the kelvins with a subscription of if the value of absolute entropy is known at the standard state pressure, the value of absolute entropy is known at the standard state pressure. Standard state pressure and given temperature. It is a straightforward procedure to calculate the entropy change from this state to another desired state following the procedure described in section 1410. If the substance is listed in table A9, we have S on desired temperature and pressure, S bar T R L N In this expression, the first term on the right side is the value from table A9. The second is the ideal gas term to account for a change in pressure from P0 to P. And the third is the term that corrects for real substance behavior as given in the generalized entropy chart in Appendix A. If the real substance behavior is to be evaluated from an equation of state or thermodynamics table of properties, the term for the change in pressure should be made to a low pressure P star at which ideal gas behavior is reasonable assumption. S star ideal gas behavior S bar T and P S bar minus R ln P star P0 Ps. If the substance is not one of those listed in table A9 and the absolute entropy is not only at the temperature T0 as given in table A10, for example, then it is necessary to calculate from S bar CP0 and then proceed with the calculation of the previous equations. If these equations is being used to calculate the absolute entropy of a substance in a region in which the ideal gas model is valid representation of the behavior of the substance, for the ideal gas model is a valid representation, then the last term on the right hand side on the equation drop out of the calculation is on the desired pressure and temperature R bar ln P on P0 for calculation of the absolute entropy of a mixture of ideal gases as T and P. The mixture entropy is given in terms of the component partial entropies as S star mix for a where S bar 0 T I R ln P on P0 For a real gas mixture, a correction can be added to the ideal gas entropy calculated from the recent equations by using a pseudo-critical method such as was discussed in section 14.10. The correct expression is S bar mix. S star, in which the second term on the right side is the correction term for the generalized entropy chart. The next section is about second law analysis of reacting system.